Let's talk about temperature. I'm sure that you've been, or people have mentioned temperature, and what are and I always start my presentations asking this question: what are the three main methods of maintaining the quality and safety of fresh and also cut produce? What's the first? What's the second? And what's the third? Even if we have a modified atmosphere package, whatever it is, we need to depend on temperature. If we have a mismanagement in temperature, even if we do not see that at that instant, long-term or mid-term, we will definitely see a negative effect. So let's start by describing what is the cold chain management. We call cold chain management the process of cooling and keeping the fruits cooled since harvest. So we start in the farm, but the question at the end of the day is, why do we do this and how do we do this? If you look at certain manuscripts or books, you're going to learn that people call, there's this name here that creates some discrepancy that we're trying to change now. It was called pre-cooling, and now we call it initial cooling. And the reason of that is just that change of word. It kind of adds to that chain, that cold management chain, that there is no such thing as pre-cooling. There's initial cooling, and cooling has to be there present since the beginning. But again, the importance of temperature management is we increase shelf life, enhance our quality, our safety. It is required for control atmosphere and modified material packaging. With this increase in shelf life, quality, and safety, we can increase our profitability, significantly reduce microbial loads. If we slow down the respiration rate of the fruits themselves, we are also slowing down the respiration of pathogenic and other microorganisms. So that's important for not only for food safety, but for the quality of the products. So of course, as an engineer, I am adamant that the refrigeration is probably one of the most significant advances of the 19th and 20th century. Actually, refrigeration was invented in 1774, and we did not see a refrigerator at home until the 1900s. So it took quite a bit for this to pick up. But long story short, who does not have a refrigerator at home? At least in the United States, I would say that 100% of the people that own or have a house have a refrigerator. So we depend on refrigerators every single day, and that's also applicable for companies. But why is this important? Let's look at this as an example. So in the y-axis, we have a percentage of marketable fruit. This is not a hypothetical example, by the way. This is a real example. We're looking at strawberries. The assumption is if we have good temperature management, we're still going to lose some marketability, but if we do not handle temperature correctly for in the case of strawberries, after like 2 hours, we've lost 20% of the marketable fruit. After 6 hours, we can lose up to 50% of that marketable fruit. And I don't mean to pinpoint at anybody, but if you go to large food or supermarkets here, in many cases, where are the strawberries as you enter? They're right there in front of the cashier. I mean, and I understand why they're doing this. They want to sell their product. They want you to see it. So if you go in the store, I'm going to get this nice strawberry that is right there. I look the other way and I go see where they're refrigerated. Don't take those strawberries. They've been there at 75 degrees, 25 degrees, 80 degrees, or in summer here, even warmer. So even if you do not see the damage of that strawberries, it will appear later on. This is a picture that I took from strawberries that were held in a supermarket. I'm not going to say their name. and you could already see moth growth, and it was right there in front of the cashier. So I avoid those if I can. As it was already probably mentioned before, the effect of temperature is typically not linear. By that, I mean, if we increase the temperature by 10 degrees Celsius, that means that we're going to increase the biological activity up to 3 or in certain cases 4 times, depending on the respiration rate of the produce. Something like a strawberry, for example, is probably along the larger end. Leafy greens, asparagus, and so on. Those are high respiration rates, so that's even larger. So that's what we know as the Q10 factor. It's or the Bank-Holtz rule indicates that the velocity of biological reactions increases from 2 to 3 or up to 4 times in some cases for a rise of 10 degrees Celsius, which is very concerning. So keeping the temperature low, earlier, the better. I'm sure Marita is going to love this example because it's a lot of her slides as well, but this just reiterates the importance of the appropriate temperature management. So let's look at the extremes here in the y-axis. It's the days for initial yellowing. Yellowing, of course, is a quality concern in broccoli. If the broccoli is held at around 0 degrees Celsius, 32 degrees Fahrenheit, it takes up to probably more than 35 days for that yellowing to appear. But if it's set at 20 degrees Celsius, right there in front of the cashier, it'll take less than a couple of days or around 2 days. And who has smelled a nice rotten broccoli? Nobody wants that either. So this is another layer. It's not only the browning or the loss of color, but also other appealing factors like you get this bad smells or whatever, and that's a problem. Like I said, off odors and so on. But today we're talking about fresh cut temperature management. I would encourage you to visit our website, and we have the typical temperatures that every product needs to be kept. And we typically differentiate between 2 different products: temperature-sensitive products and not temperature-sensitive, or whatever. Not temperature-sensitive products are typically tropical fruits, cucumber, tomato, papaya, and so on. And it's encouraged to keep this produce at a slightly higher temperature, around 10 degrees Celsius, while all the other non-temperature sensitive products very close to 0 degrees or even below. I had a question. I gave this talk, and it's like, well, somebody told me that I shouldn't refrigerate my tomatoes. And that is accurate. If you refrigerate your tomatoes at 4 degrees Celsius, like we typically keep the refrigerator at home, we will see, some issues. But if we would have the ability of having a refrigerator that has the temperature around 10 degrees Celsius, of course we could refrigerate the tomatoes. So it's dependent on the temperature, and you need to rely on that and look at the best ways of storing temperature. It's slightly different when it comes to fresh cut temperature management. Once we remove the peel, once we've cut into the skin or the flesh of the fruits or vegetables, we're completely changing the biological structure of this. So we're already enhancing browning, there's softening of the tissues, deterioration, a significant increase in microbial load. We have all those sugars available, for microbes to grow and so on. Change in respiratory rates as well. So we're exposing those cells, then they probably transpire much more or less. There's oxidation, and et cetera, et cetera. I can continue this list. Therefore, it's recommended for fresh cut items that should be stored between 0 and 5 degrees Celsius, regardless if they are categorized as temperature sensitive or not, with some exceptions, of course, and probably Marita and everybody here can contribute on why those exceptions might be here, or if they're even valid for what I'm saying. But in some cases, squash, cucumbers, watermelon pieces need to be stored slightly higher, but still not at 10 degrees Celsius as it's specified. One concern if I put a watermelon piece in the refrigerator and it's too cold, it's going to freeze and it's probably going to lose that appeal. So that's probably one reason highly watery items probably slightly higher, but still you need to control the temperature. But where does cooling begin? I said initial cooling is typically in a plant, but where does cooling really begin? Where would you say? Sorry? In the farm. So does that mean that we need to have a bunch of refrigerators in the farm? So how can we start cooling in the farm? Yes?
Well, harvest in the middle of the day, harvest when it's cooler out.
Yes, exactly. So if we plan right in a shaded area, for example, in a nice summery day here in California, it could be 105 degrees in direct sun and around 85 degrees in the shade. So there's a huge difference. So cooling begins in the farm, it begins in the field, and there's no recipe of how cooling starts. It's just as producers, you need to be aware that this is a requirement. And the earlier you start, the better. And each location is different. In many cases, fruits and vegetables are even harvested at night. Not even the crews come in there at night. Why? Because they want to keep them colder and fresher. So cooling begins in the farm, and there's many, many ways of doing this. I took this picture somewhere in Salinas, actually in Bakersfield, I'm wrong. And you can see that they have a structure, in the back of a flatbed truck with a shaded area, and that's meant to protect them from the sun. As you mentioned, not only prevent that heating during harvested with shades, but also shorten time before cooling begins. Use frequent scheduling. The schedule of harvesting could be at night and so on to enhance that. This is a carrot receiving facility that use water. As water soaks the carrots, there's some evaporating cooling effect, and therefore you get a reduction in temperature and some cooling. And look at this. This is the truck that is right there. And as they're harvesting, all their boxes are right there in the sun. Those are the type of eyes that you guys need to, have when you go out there in the field. Okay, you're doing it okay right here, but probably we should have an additional structure that could protect these ones as well. Of course, if you ask them, they probably tell you they're only there for a couple minutes. I counted, and they were there for 5-10 minutes. So be diligent. That's what I mean. So in other words, this versus this is probably better. And somebody's pulled my ear sometimes because really this is not ideal. And why wouldn't it be ideal? This one right here, even though it's in the shade. Probably give prices to whoever, except for Marita. Bird poop. Those beautiful birds. Well, food safety, So we also need to be aware. I am, as an engineer, a lot of times not aware of food safety, but I'm not that brilliant either. So there you go. So as I said, where does cooling begin? It always begins in the farm, and it begins with you guys. It begins with you understanding the temperature is important and aware of where this starts. And as I said, the recommended peak to cool times vary depending on the type of crop. It's something that has a fairly large respiration rate, like strawberries and grapes. The accepted delay is 2 hours or less. Something like garlic, dry onions, potatoes that even go through a curing process, you can afford to take a little bit longer. But bear in mind, the sooner the better. So how important is relative humidity in comparison to temperature? Why are people not mentioning relative humidity? I've been asked this. My cooler, I don't care at what temperature it is, but I get all my floors wet. They're soaked with water, so I'm not losing any moisture. Is that accurate? Really? Who would say that's okay? I don't care about temperature management because there's water particles everywhere and I'm getting no moisture loss, if that's what you're aiming for. Well, psychrometrics showed us that that's not the case. Let's look at the effect of temperature in comparison with relative humidity. Basically, what we need to look here, and this is really crowded, I'm sorry, and we don't have a lot of time to explain this little guy here. If you want to learn how to use this exhaustively, come to our short course. We show you a whole afternoon of how to use psychrometrics. So, and that's actually, it's really nice to learn this. But the take-home message is that the loss of product weight is directly proportional to the difference between the vapor pressure of the product. The vapor pressure is in the y-axis here, wherever it went. Right here, that's the vapor pressure. So the larger that vapor pressure differential with the environment, the more water we will lose. Okay? The product, we can assume this. We can assume that the product is at 100% relative humidity. Why? Because the majority of fresh produce have around 90% moisture or moisture content or higher. So our assumption is that our product is at around 100% relative humidity. The relative humidity in the environment may vary, and the temperature, of course, may vary. But let's assume that our cold room is at around, so in this case, around 0 degrees Celsius. And our product, if we place an apple at 20 degrees Celsius, eventually that apple is going to equilibrate with the cold room. So the loss in water is equivalent to that bar. That's where the fruit is, 100% relative humidity. The cold room could be at 100% relative humidity at around 0 degrees Celsius, which is here, and we're still going to lose all that water. If it's at 5 degrees Celsius, we harvest in the morning, it's earlier, we have good initial cooling, then we're losing moisture equivalent to this bar right here, significantly lower. Can you show me my number again? 10 minutes. Perfect, thanks. So I just lost. But let's assume, and I'll move here, that the relative humidity of that room is, let's say, 80 or 90%. Still, look at what is the effect of relative humidity within that room. It's almost insignificant. Even if we keep it at 100% relative humidity, we're still going to lose a significant amount of moisture if we are not cooling our product correctly initially. So, when all these experts right here have told you that temperature is the most important, it's because it is. It's psychrometrics. And that, as an engineer, I understand. So considerations for optimum cooling, and you might add to this, we've said this, minimize the time between harvest and cooling, harvest early when it's colder, not in the middle of the day. The type of packaging is also important. This is the #1 frustration for me as a post-harvest engineer. When you visit facilities and they tell you, I'm doing everything right, and I'm not seeing any cooling within my packages. You look at their packages and they have no air void spaces. So it's like all your package is nice and sweaty in there, but you're not allowing the air to flow through it. So at least a 5% minimum of ventilation. Type of cooling and required time varies from crop to crop. Initial product temperature, final product temperature, all these are questions that we need to ask when we're cooling. Water chlorination, pH, and equipment cleaning, which is a must for food safety. The product temperature requirements, we briefly talked about temperature sensitive and not temperature sensitive product. Susceptibility to water. There's some products like that are more susceptible to water than others. For example, strawberries tend to be highly susceptible. I also did a study here that in California, they were dipping cherries in water for cooling purposes, and this would enhance the splitting of the cherry, so that's a quality concern. As it absorbs all that water, it caused splitting. So you need to consider what type of product. Not everything is cooled the same way. And as I said, probably many more. This list can be much larger. So let's look at the different cooling types that we have here. Everybody knows the room is acting like a refrigerator. There's other methods: hydrocooling, liquid ice, vacuum cooling, forced air, and during transportation. Question: do you think that during transportation we see any cooling? Cooling effect during transportation. So let's say that I put a product and I don't care because I'm going to put my product in a trailer that is refrigerated, so I don't need to initially cool in my factory. Is that accurate? No. Actually, we see increases in temperature during transportation in certain cases, if product is not initially cooled correctly. The heat within the product, and if it hasn't been cooled, you will not see a decrease in temperature during transportation. There's some exceptions, so it depends. Maritime, so boats, those have the ability to, in certain cases, reduce the temperature of the product. But generally speaking, trucks, trailers, refrigerated trailers, because of the size of the refrigerating units and the setting and the sizing and so on, it's not doable. It could happen in some cases, in some instances, but generally speaking, before we even transport our product, it needs to be cooled to the desired storage level. Okay? So do not rely on transportation to cool your product. We talked about optimal ventilation. Here we have a perfect example where there is basically no ventilation in this package right here, and this one optimum at around 5%. So you will see a significant better cooling here in comparison to these boxes right here. Typical cooling curves, you'll hear this quite frequently. 7/8 cooled, it's just basically in relationship to the initial produce temperature. So if we have an apple going into our cooler at around 25 degrees Celsius, half of that is, or half cooled, 12.5, a half of that is 3/4, and a half of that is 7/8. So the expectation is that we need to design the system or the refrigerator unit to be able to achieve this type of curve when we're cooling. And that's why the majority of refrigerator units are designed, using this 7/8 of initial produce temperature set point. So we talked about cooling during transportation, and as we mentioned, product temperature drops is rare in trailers. If you learned something today, I'm happy if this is what you learned. Slow cooling during marine transportation, but it's typically, it's not, you don't need to depend on this either. Room cooling, and the reason why we have other methods of initial cooling is, let's look at these numbers right here. So if I put an apple in the refrigerator, of course it's a small unit, but if I put it in a large refrigerated unit, it could take between 18, 90 hours, or in many cases, you will never achieve the 7/8 cooling just because the air is stagnant within that room. So just placing fruits, vegetables, fresh fruits, vegetables within a cold room, it's not useless. It's better than it being outside, but that cooling rate doesn't exist. But how can we achieve this? What do you do in a warm day? This, okay, airflow. What are we doing? We're getting all this nice cold air. We're enhancing, with our sweat, there's some evaporating cooling, but basically this cools, okay? So that's the concept of forced air cooling. Look at the difference in time. Cooling time for 7/8, depending on the products, can be between 1 to 10 hours. Moisture loss between 0.1 and 2%, in certain cases slightly higher, depending on the product. Here we have much higher moisture loss. And we know that because the product is kept at a higher temperature for longer. So just by forcing air through the boxes, typically how this is done is you have this tarp that creates a pressure differential within that separation of two bins or two rows of product. And you're very simplistically using a fan to force air through the boxes. This is a concept that is not only used in refrigeration, it's used in drying and many other, depending on the conditions of the air, we can achieve many, many things. So, typically, as I said, this is kind of a top view. We have a fan. Now the systems, you have the ability of changing the direction of that flow. The reason behind that is so that you can achieve higher uniformity when it comes to cooling and so on. So you could see this in practice now. As I said, moisture loss in forced air cooling varies and is typically dependent to the size for the temperature drop of that cooling. So in this case, it was carrots without tops. Weight loss was depending on how much you wanted to drop the temperature. So higher temperature drops, or where you get that higher temperature differential, you tend to lose more moisture. Hydrocooling, as its word says, we're cooling with water. There's mobile hydrocoolers. You've probably seen many versions of this. Immersion hydrocooler, like the one I'm showing here. In many cases, you do not see moisture loss, but you see moisture gain. I said the story of the cherries. Cooling is very, very fast, 5 to 60 minutes, and I think that 50 minutes there is probably overdoing it for the type of products that we cool. It's mainly dependent on the product diameter. So larger diameter like cantaloupes can take many minutes, and compared to something small like a carrot, a radish, a cherry, or whatever. So you need to put important to pH and chlorine levels, mainly for food safety. So that's another consideration when you're doing hydrocooling. Same consideration when you're doing ice or liquid ice or top ice cooling. This is a method that is broadly used in broccoli and others, where you have this automatic liquid ice that injects or forces the ice through the boxes. Moisture loss is almost non-existent, and cooling times can be 6 to 20 minutes, and I have here top icing can take much longer, so just placing it in ice, not doing anything, but forcing this liquid ice through the boxes, very fast rates of cooling. Vacuum cooling, this is my favorite of all. We use the concept of if we change the pressure of the product, and therefore by reducing that pressure, the water evaporates at much lower temperatures. So in this case, water evaporates or boils right here at around 100 degrees Celsius, 200 degrees Fahrenheit. But if we lower the pressure to almost perfect vacuum, 0.02 atmospheres, water would evaporate at near freezing. So when water evaporates, you get that immediate cooling effect. Problem is that water needs to evaporate, so moisture losses are fairly high. But what we've learned is that the better the controllers now and how we've set everything, this is changing quite drastically. We have much better computerized controls and so on to be able to do this. This is just the typical romaine lettuce vacuum cooling. After 30 minutes, pretty much the cooling is finalized. You can start at very high or fairly high temperatures, 50 degrees. After 30 minutes, you've below 35 degrees Fahrenheit. Typical times, we have 2 to 4 hours for very dense products, but it is fast. Like leafy greens, like spinaches, it should be done in minutes. There's water spray vacuum cooling units that are also available, which can take taken in theory from location to location, and the reason why they wet the product is because they want to reduce that moisture loss. Capital cost, liquid ice is the most expensive at this point. Hydrocooling would be the less expensive. This is probably going to change with the changes in water availability and so on. Vacuum cooling and forced air cooling are in between there. Energy use, so the energy coefficient, the higher the energy coefficient, the better energy usage, or the most energy efficient it is. So forced air cooling is reported to be the less efficient. Why is that? And I'll end my talk there. Time, yes, that's the main reason. Actually, for forced air cooling, regardless if we are cooling or not, we need to have the refrigerator unit on. So it takes much longer time to cool. On the other hand, vacuum cooling, you're sitting in your nice office and you're just hitting the vacuum, cools for 15, 20 minutes, and then you turn everything off. So very highly efficient. And all of the others are in between. And you're going to have access to this so you can see that. You cannot manage temperature unless you measure temperature. There's no excuse for you guys not to measure temperature. The world is the limit now with all the offerings that we get of different ways of measuring temperature. So if you tell me that you cannot afford a $2 a thermometer, we're in problems. But you should be able to measure this, okay? And with that, I thank you, and I'm open to questions. I don't think we have time, though. But thank you very much.